So a small thing, when you have a reflection, uh, if the angle of incidence is very low, okay, and the angle of incidence can be treated on this side. I mean, the ray between the angle between the ray and the vertical line, or the angle. I mean, consider the horizontal line as the ground or something. So the other option is the and ray angle between the ray and the horizontal line. Okay. So we will consider the angle of incidence as the angle between the ray and the horizontal line. If this angle is low, then I mean, without any proof, actually, we are showing this relationship that this EI and ER, okay, they will be equal. I mean, in their direction will be the same. The proof we could show, actually it requires the explanation of a diagram, and I assume it will be shown in the course of fields and waves. Okay, and that explains, I mean, when the ray arrives with a particular polarization and it is incident on the reflector, then after reflection, how the angle, how the orientation of the electric field changes. Okay, so anyway, I mean, we are considering solar reflection. Okay, there is no component going into the material. Anyway, if we have a vertical polarization, meaning that this ray, this is the direction of propagation of the whole wave, but the electric field is in the vertical direction. Okay, the electric field is in the vertical direction for the angle of for the ray which is incident, and then the reflected component will again have the electric field in the vertical direction. Okay, I mean, it is in the vertical direction, but I mean, if it is say upwards, after reflection it is also upwards. Okay, but if we have a horizontal polarization, then there will be a change of angle by 180 degree. Okay, so if it was upward here, after reflection it will change, it will be downward. I mean, of course it's changing sinusoidally, but the reflection will cause a change of angle or a change of phase by 180 degree. Okay, so that can be explained with explanation of a diagram. Okay, however, if it is not explained in the fields and webs course, you can let me know and I can explain here. Now, in the last class, we said that this, I mean, horizontal line is is representing the ground, acting as a good reflector. So from A, the direct wave is getting to the receiver C. Now the actual distance between the two towers is BD, which we consider D. But this AC, okay, will be little different because the tower heights are not the same. Okay. In this figure, the transmitter height is little higher. Okay, it's a little more. So we have HT as the transmitter height and HR as the receiver height. Okay, so AC is D prime, and that is the distance for the direct wave. It will cover, the direct wave will travel covering a distance of d prime. Now the reflected wave will first cover a distance AO, then after reflection OC. So the total distance AO plus SOC we consider to be D double prime. Okay. So there's the reflecting component reflect from the ground, we call it EG, and this is the direct wave via an LOS path, so we call it ELOS. An image, let's consider here below the ground plane. And also we mark a point X with a height HR on the transmitting side. Okay, so we have a triangle with a right angle here. So we consider that this assumption is true there. Okay, we have a small angle of incidence, and we consider here to match with our derivation of in the book of Rappaport, we consider here horizontal polarization. Okay, so there will be a change of angle or change of phase, or change of phase by 180 degree. Okay, now for LOS component, okay, for this direct component, if we write down an expression for of wave, then we showed this expression before, that there's a function of wave we consider for electromagnetic wave, and if we consider a sinusoid, okay, the signal will actually be say for communication, you are sending some information, so the overall signal is non-sinusoidal, but you can split it into Fourier components, and each component is a sinusoid. So let us work with one of these sinusoid components. So you have cos omega t minus t prime. Okay, there's the total distance. The speed is the speed of light, c.
So,
yeah.
Can you please start from EG, how you get the derivation there?
Sorry?
Can you please start from EG, the first
yeah.
one?
Yeah, I will talk about EG, but we first talk about ELOS. Okay. So for ELOS, this is the direct component. We have now here we considered the electric field at a reference distance d naught. Okay, and then for your particular desired distance, it is shown this way. Okay. So we can call it here E naught, okay, which is the E at the distance of d naught. So we call it E naught, and then multiply by d naught and divide by your desired distance, which is d prime. So you get the total E. There's the amplitude of your E. So this is the total wave, your amplitude, and so this gives you the instantaneous value of ELOS. And so E naught is the maximum or amplitude at a different distance d naught. Now, for the reflected component, okay, we are covering a different distance d double prime. Secondly, we'll have a negative sign added here. Okay, so these are the two differences. So for EG, we change the distance to d double prime, and we add a negative sign, okay, which is the change of angle at the point of reflection. At the point of reflection, there's a change of phase by 190 degree. Okay, so these are the two electric field components getting to the receiver. So the receiver will receive a summation of these two. Very simple. Let's just sum up, okay, these two. Now we'll find out some equivalences like AO plus OC. Okay, this whole thing, or D double prime, we can also show on the image side. Okay, this AO and EO will be equal because we have drawn an image here. AB and BE are equal. Okay, so EO plus OC or EC. Okay, so that is our D double prime. Now EC we can show as because we have an angle here with right, we have a triangle with right angle, EXC. Okay, so EC we can show as EX square plus CX square, then root. EX square plus CX square, then root. Now CX is actually the distance D. It's equal to BD, the distance D. And EX is actually EB plus BX, where EB is equal to AB or HT, the transmitter height, and BX is the receiver height, HR. So we get here EX HT plus HR whole square, and then D square for CX square. Okay, so D prime we get in terms of HT, HR, and T. Similarly, for D prime, we can get an expression AX square plus CX square and then root. Okay. Now here CX is equal to D and AX equal to AB minus BX. So HT minus HR plus AX. So we can write HT minus HR square. Okay. Now what is important here is the path difference, because we have a summation of two different signals, and there is a phase difference. Okay, as they arrive, they come with different phase. Now, the summation depends on the phase difference. Okay, if they were in phase, then we would just simply add. If they were completely 180-degree out of phase, we would simply subtract. And in the angles between these two extreme points, okay, will actually dictate how you get the summation. And see, the angle difference actually depends on the path difference. In other words, as the signal is traveling, you have a continuous change of phase. And it is propagating, you have a change of phase. Okay. Now, when it covers two different paths, then in the course of change of phase, they will appear with two different phase positions when they get to some point. Okay, this guy is changing phase, this guy is changing phase as they propagate. But since the path is different, if the paths were the same, were equal, okay, different but equal, then okay, you would get the same phase. But because this path is larger, it will appear with a different phase. And that is actually clearly shown in the equation, that it is, you have here a phase omega d prime by c, here omega double d prime c. That's how we see the phase difference. So we also mark the path difference, okay, by delta to relate it to the phase difference. So delta is d prime minus d, And for that, we can have now this equation, okay? Very long expression here. But if we use Taylor series if you just expand with Taylor series, okay? I haven't shown this step here, but actually if you try, you can do that. So if you, and after the expansion, if you use this approximation that the distance is very large compared to the tower heights, which is typically the case for long distance terrestrial communication. Okay. Then delta can be approximately equal to this term. Okay. Now, before we go further, let me tell you that this particular model is widely used for long distance terrestrial communication. Okay. So there, when you say um, the rural areas, okay, uh, in this or open have open uh, fields, and as you get out of the suburb area, then and you want to cover uh, long distance to connect some distant locations, like when you route the voice calls in our landline system, okay, to some other district. Like if you are calling someone in, say, Tangail or something, okay, or Bogra or something. So the calls are routed via long distance um, communication towers. And as you leave the core Dhaka, you actually find some open areas. So you have high towers, okay, because you have to connect uh, over the obstacles and establish an LOS link, which demonstrated in the lab class why you need that. And that's why you see that we have very high towers at Mokbajar Exchange, okay, and also at Banani. So they route calls to different districts. However, you need some repeaters on the way because the distance cannot be too long. You will have signal degradation. We know that the longer distance uh, the, reduces the power level. So the typical distance used in our country is around 40 kilometers. Actually, that's pretty much the convention in other countries too. It is around 40 kilometers. Okay. So, but that's a long distance. Okay. Uh, if although the tower height is okay, that's also significant. Okay, but with this, comparing to this long distance, 40 kilometers, okay, it is actually very small. So in this case, this type of models is required because then you don't have obstacles on the way to stop the second ray within the suburb area. Okay, it is there are buildings, a lot of buildings, okay, uh, densely located buildings. So you cannot actually get the second ray. They will be obstructed by buildings. But when you leave the suburb area, you find open areas. You leave the urban areas, sorry. You leave the urban areas, even in the suburb areas, or, sorry, mistakenly I was mentioning suburb. Okay. Once you leave the urban areas, even in the suburb areas, and of course in the rural areas, you will get the second ray, okay, because of the lack of buildings. Okay, it is quite likely that a second ray will be possible. Okay, you will get a reflection from the ground, and that causes a good power level, okay, because the ground acts as a good reflector. So you cannot actually ignore this second ray. It comes with very good power level. And that is why this two-ray model is so important. Okay, so very commonly you get this case, you get this scenario. Okay, now we are interested in the power that we received at the other end. That's why we are doing all these derivations. So let's calculate the electric field at the receiving end. Once we have electric field, we know that, I mean, we can find out the power to E squared by eta can give you the power. For electric field, we have to sum up these two, and there's a phase difference. Okay, and so if we show in phasor form, okay, let's assume that this is the reference phase, 0 degree, and the phase difference is theta del. Okay, so for this, for the first term, the angle is theta del. So this is what you have here. And theta del, okay, is actually omega d prime, omega double d prime by c minus omega d prime by c. Okay, so that is equal to omega c into d prime minus d, which is del. Okay, now for del, we have an expression here, 2 HTHR by d. So you can put that. And for omega, we can write down 2 pi f. For c, we can write down f lambda. We can cancel f. So we have here 2 pi and here 2 ht. So we get 4 pi by lambda HTHR by d. Okay, so that is our theta del. Now, the amplitude levels, if you compare, will have insignificant differences because I mean d prime, and when you consider d much larger compared to HTHR, okay, d and d prime are not too different. Okay, so for the amplitude levels, let's just approximate to them to be equal. And the phase difference now matters, 0 degree and theta del. Okay, sorry, I lost the connection. Okay, now let's consider two vectors, A and B. If you subtract B from A, okay, say A minus B, then you can actually write down this A minus B this way, that you take A cos theta. I mean, theta is the angle between uh, uh, I mean, theta is the angle here on the right side. Okay. So, I mean, you can write down A vector plus minus B vector. Okay. A vector minus B vector. Let's show it on the figure. This way, that A vector plus minus B vector. And then you split into two components. Okay. The horizontal and the vertical. So on the horizontal side, you take the component of A, it is A cos theta. Theta is the angle here between, on the right side, between the A vector and minus B vector. Okay, so A cos theta and minus B. Okay. Then there's the horizontal after you take the part, and A sin theta is the vertical part. Okay. So if you take the square of this two and take the root, that will be the actual, that will be A minus B. So this is what we want to do here. I mean, I mean, this is our A, and this one okay, is our B. So I mean A cos theta minus B whole square plus uh, A, sorry, A sin theta. Okay, this one A sin theta whole square. Okay, then E naught D naught by D we can bring outside. And for the rest, if you just expand, okay, some manipulation, then it ends up with this expression. Okay, so E total equal to 2 into E naught D naught by D sine theta by 2. So it shows that E total um, varies in a oscillatory fashion. Okay, of course, as you increase D, it will keep decaying, but there is also an oscillatory variation. Because as you keep changing the distance, if you keep changing, if I keep changing D, okay, the distance between the transmitter and the receiver, the total electric field, the electric field that we receive at the receiving point, will have a variation which is oscillatory decay. Okay, it is reducing, but there is a small oscillation, sinusoidal variation. Okay, because of the sinusoidal term. However, for a very large D, again another approximation we can do if our D is very large. Okay, then theta will be very small. Okay, the path difference will be negligible. Theta will be negligible. So then, it depends on the comparison between the heights and the distance. So if the distance is too large compared to the tower heights, then you can do this comparison. Okay, sin theta del by 2 equal to theta del by 2. Now we assume that this assumption you can use if theta del by 2 is less than 0.3 radian. Okay, but for theta del, we have this expression. So in terms of those values, we have a limit for our approximation, that this one has to be lower than this value. In other words, D has to be larger than this value, 20, which is roughly equal to 20 STHR by lambda. So in the problems, you may have to first check whether you can use this approximation or not. So STHR and lambda may be given. If frequency is given, then I assume that you can get lambda. So you calculate 20 STHR by lambda, and then you check, you compare with D. If D is larger, then you can use this approximation. If D is smaller than this value, then don't do the approximation. So two different cases, if it is larger or if it is not. Well, if it is larger, then you consider here theta del by 2, and so your E total will be 2 E naught D naught by D into theta del by 2, which is for theta del, we have this expression. So just divide that by 2, okay? You get this total term. But if it is smaller, then you have to keep the sine term. You have to keep the sine term. Okay. Now from this electric field values, we will calculate our power values. We know that the available power in the air will be E squared by eta. And if you multiply that with the effective aperture of the antenna, then you get the power received. So E squared by eta into AE. But for AE, we have this expression. Okay. So this is what we have for the total power. And for E total, we have two different expressions for two different cases. First, we consider the first case where the approximation is possible. Then put the value of E total. Okay. And here, I mean, we have 1 over eta, then gr lambda square by 4 pi. Lambda square you can cancel. Okay. Now another way we can actually simplify, although it is sort of approximation. See, you know that if it was a free space case, okay, then what we get, say ptgt by 4 pi d square. Okay, just go back to our early discussion, free space equation. Okay. In this case, what we had, ptgt by 4 pi d naught square, okay, can give you the, we are considering the reference distance. Okay, so at that reference distance, the power density will be ptgt by 4 pi d square, we know. Okay, and that will be equal to E naught square by eta, right? So if we have just a single ray component free space case, then ptgt by 4 pi d square will be E square by eta at that distance. Okay. In other words, for ptgt by 4 pi, we'll have this expression. So let us approximately consider that we can use this equivalent, I mean equivalency, and replace E naught square d naught square by eta by ptgt by 4 pi. Okay, so let's do that. E naught square d naught square by eta, we're replacing by ptgt by 4 pi. Okay, again we can cancel this 4 with 16 and pi square with this pi. I mean, we also have pi square in the denominator. So eventually we get this simple relationship, Pr equal to ptgt gr by ht square hr square d to the power 4. Okay. However, for the other case, when d is smaller, then you have to keep the sign term. Okay. So E square by eta and g lambda square by 4 pi gives you this relationship. Okay. So again, you use E naught square d naught square by eta equal to ptgt by 4 pi. Okay. That little bit simplifies, but we end up with this longer expression. Okay. So in the problem, once you check whether or not you can apply this approximation, you decide which equation you have to use for receipt power calculation. Okay, if this one satisfies, you use this expression. If it doesn't, use this second expression. Okay. I would like you to memorize this. Well, in this course, you won't have to memorize too many things, but a few simple relationships I would like you to memorize, because as a wireless engineer, you should remember this, I mean, few simple relationships. Okay. However, if we have an online exam, then it will be open book. So you can actually get the help from the notes directly. But if we get an exam anyway with physical presence, then you know it will be closed book exam. And then this formula you have to have in memory to answer the questions. Okay, the first relationship is more common because usually the distance is larger. Okay, when the second ray is possible, the whole derivation is applicable when you have two rays, second ray reflected from the ground. Okay, this way. And uh, typically you have them with large distance. Okay, so you have a change of power with distance where it is varying uh, inversely proportional to d to the power 4. Okay, so if you compare with our one ray condition, the direct ray condition, then we have a inversely proportional relationship with d square, here. Now, with the presence of the second ray, it is inversely proportional to d to the power 4. Okay, so as we change the distance, now it is changing with 1 over d to the power 4. So if, like before, if you work this way, that at a reference distance, you calculate or you measure, the measurement will give you more practical results. Okay, and mark this power level, PR at D naught. Then for other distances, you can directly calculate. Okay, when D is large, you can directly calculate using this relationship. So PR is inversely proportional to d to the power 4. And if you consider the path loss, how much energy you lose on the way, that is our PL. PL stands for path loss. Then it is proportional to d to the power 4, okay, right? And path loss is increasing, the power that you lose on the way. Okay, like here, PR is proportional to d square, but PL is proportional to d square. Okay. Okay. That pretty much completes the discussion. But one simple thing that you see that we have considered two cases, okay, and we found the power to decay with the change of d as a, I mean, with inversely proportional relationship with d square and d to the power 4. So it's some exponent of d. Okay. So practically, you have a path loss like that. Okay. Uh, uh, it is some exponent of d. Okay. If we write down, you can write down in terms of PR or in terms of PL. So if I want to write down in terms of PL, okay, then the expressions that you use actually called path loss model. Okay, so the expression that you use to represent path loss or energy loss on the way is called path loss model. The two expressions we have derived actually also represent path loss models. And there are many other path loss models. Okay, well, like more than 100 path loss models are available these days. And you can select the right one for your particular environment. Path loss models are also available for non-LOS case. Now, in practice, you can have many different objects around in a particular environment, and for all these environments, you'll find the path loss to vary, but this d will have just some different exponents. Okay, 2 is the smallest, and 4 is also, I mean, pretty high level, but it can be even higher. But when you have many other reflected rays or diffracted or rays coming from scattering, however, because of the presence of many different objects around, you get many other rays. So for this, the overall path loss will be some power of, I mean, will have some exponent of d. So in general, we can say that PL, okay, will have this relationship where the exponent I mean, we just show as some variable n, and for a particular environment, you can just try to find out its value. Maybe you do some experiments, take the receipt power levels at different distances, and then you calculate the path loss, okay? And then just extrapolate and find out what the value of your exponent. Okay. So a common model we can use, and it is called log distance model, because I mean you're using dB here. Okay, I mean it's shown in dB form usually. So you have logarithm, and with log term you have 10n log d by d naught. You just, for your environment, you just have to find out the value of n. Later we will discuss many other models, and then we'll see. I'll also see that you can consider some random variation. Okay, I mean there'll be some statistically distributed variation you can also consider. Okay, because these are some probabilistic case. Okay. Uh, anyway, the table 4.2, okay, gives you I mean tabulates the value of n for different types of environments, like say some factory area, okay, or some probably some shopping complex, or different types of, for different types of environments, the value of n is tabulated there. Okay. Okay, now do you have any questions?
No, sir. It's okay, sir.
Okay, so we'll move on to our next discussion. We assume that we have completed.
So this derivation that we just saw, sir, like the effect of reflection, sir, in this ground Turing model, sir. So do we have to like know how this all these formulas are derived for the exam, sir? Is it like the entire thing, or will you be giving like parts of it in order for us to uh, write in the exam?
Well, I don't know.
Okay.
uh, I said the questions at the last minute.
Yes,
Okay,
sir.
so actually, I don't know how I will prepare the questions, but when I prepare the questions, I just consider that everything we covered in the class, okay, you should know well.
Yes, sir.
And if it is, I mean, open book exam, then you have the materials. I mean, also keep in mind that you have all these class notes available. Okay,
Yes.
so that you have to answer. If I just ask you to write down the whole derivation,
Exactly, sir. It's
then
very easy, sir.
you
Then it
can,
is open book.
yeah.
Yes.
So even, I mean, you can just ask your young brother to to write it down for you. Okay,
Yes.
who may be studying at grade 4 or 5. Okay,
Exactly, sir. That is just I was
so
asking. So, sir, like, how will the questions for it
yeah,
be like, sir? Yes, sir.
yeah.
So,
So
from here,
so I just have to consider all these things and
yes.
then prepare the questions, but I don't know how that might be. Okay.
So, please give us a head start, sir, because in the example, sir, if we see something and it is like completely
So for example, if
something
I,
unexpected, yes, sir, you
well,
can answer.
if I give you some problems that use the expressions,
Yes,
then of course you have to work out. And if I give different values for different students, maybe the values that you work with, you first have to calculate using your student number, last digits
yes,
of student number. Okay,
yes, sir.
then that can differentiate the answers. So you may have to work out. And um, also sometimes I can ask some short questions. Okay,
Yes,
testing your concept. Okay, that what is derived here, whether or not you um, have understood them clearly. Okay, So I have explained, okay?
Yes,
But,
that you
but
did.
if you're attentive, then you have actually understood. Okay. If you're not attentive, then you haven't. So I may test these things too. Okay, our next discussion will be on diffraction.
So before this, will you take the attendance? Because the last class I wrote in the comment section.
Oh,
Sir, that
really?
yes, sir.
Mm.
That last class also the attendance was skipped, sir. So
Yeah, yeah. Thank you very much.
no
Thank
problem.
you But you know what? The students who are missing the class, okay, will
Yes,
later nab you. Okay. Why? Why you reminded?
That's my
sorry.
fault. So Tasin, it's your duty to wake them up who are sleeping.
Oh, करते घूमते
Yeah.
उठते. Okay, sir. First person is awake, sir. Yes.
Oh, yeah.
Job well done.
Yeah. Yeah.
I was awake.
I was, sir.
Okay. Okay, it is already there in the classroom. Please,
Okay, sir. Okay, sir.
right. Now, do you see the slide for diffraction? Is it visible?
Yes, sir.
Okay. Now, the actual principle will not explain. Probably some physics class have explained the diffraction principle. Once the electromagnetic wave is incident on an edge, okay, sharp edge, then a number of small waves are created from there. And these are called wavelets because these are small waves. And they travel in different directions. Okay. So many different small waves created as if you have new sources of waves. Okay. Like, I mean, when you have some emission from a source, the wave just travel from there. Okay. From the source, they start and they keep traveling. But when when they are incident on a sharp edge, then as if you have new sources are created there on the edge. So new waves will be created, and these waves will have different directions of propagation. So these, wavelets together form a wide angle, okay, of new propagation, and that can cover many receivers, or that can make it possible that people will receive the signal at many different locations. So this can help wireless engineers, and so we need to know how much energy can really be possible. Okay. I'm sorry, I was struggling with my writing pad this morning again, but it's not. I updated the driver and okay, did a few things, but it is not showing all the windows. Okay.
So did you try uninstalling and then reinstalling the drivers?
Okay, I'll do it before the next class.
That might help.
Yeah, I know that it's okay. I know that it is we are in dire need of something. Okay, so inshallah, let's see if we can make it work. Now we will use a model where we consider that between the transmitter and the receiver, again with HT and HR heights, we have an obstacle. Okay, and the top of the obstacle has a sharp edge. Since we're looking at from one side, I mean it's a 2D diagram. It's not clear, but let's consider a like say if it is a building, okay, then you have actually long edge, vertical to this 2D plane. Okay. So the top edge of the building can have diffraction, and so from the transmitter point T, the signal will be incident on A, and then the diffracted wave can will have different directions, but we are interested in the component that is traveling towards R. Okay, so AR will be the path for the diffracted component. Now we would like to derive how much power we get at the point of R because of diffraction. Okay, that's the whole purpose of this discussion. But it also depends on the path difference, where by path difference I mean the path between TR and the path AT plus AR. Say for the diffracted power, okay, the total path the signal is covering is TA plus AR. But we compare it with the path TR because this if we had a clear path there, if we did not have an abstraction, there would be a direct ray possible along TR, and we clearly understand how the power level would be there. Okay, so actually this power level calculation for diffracted ray is calculated in terms of that power reception. Okay, I mean say power via TR, power over a distance D1 D2. Here D1 is the distance between transmitter and the obstacle, and D2 is the distance between the receiver and the obstacle. Okay, so I mean the free space case could give you how much power you get at R if you did not have, or if you even had a large hole here in your obstruction, you could get a direct ray, and you know how much power you would get there. Okay, so our power calculation will actually use this relation, this comparison, and give you okay what power you get here compared to that. Okay, you don't have this hole here, okay, but you first have to calculate this power and then add something to that, okay, to get what power you get here. Okay, so I mean we are also considering here the path difference. Okay, we call it excess path length. So that is, you know, I mean AT plus AR minus TR. Now, if you do some approximation, then for AT, okay, you can write down, I mean, we can consider here a triangle with right angle, okay, approximately. So then H is here the high, well, it is very important to understand what we mean by H, okay. If you connect T and R, you just draw a line between T and R, and then you find out the height above of the obstruction above TR, then it is your H. Okay, I mean, in this whole discussion, the H notation will indicate the height above TR, height of the obstruction above TR. Okay. Now, AT we can write down as d1 square plus h square and then root. Okay, just assuming approximately a triangle with right angle. Similarly, on this side also AR, okay, will approximately consider to be equal to h square plus d2 square and then root. For TR, we have a distance d1 plus d2. Okay. Again, I mean, you can say that, well, if you measure the distance on the ground, okay, then you don't have this inclination. And so d1 and d2 would be different, but we consider them to be equal approximately. Okay, you might be measuring the distances on the ground, but you just assume that when you draw TR, you have the same values for D1 and D2 parts within TR.
Sir, I didn't get
Yeah.
your last point, sir.
Oh,
You
So
broke
we
away a
ignore the
little, sir.
inclination.
Yes.
sorry.
Will we ignore the inclination of TR?
Yeah, yeah. I mean, you consider we don't. I mean, the inclination is there,
Yes.
but when we consider the value of D1 or D2, okay, D1 is the part of the first part of TR.
First part of TR. Yes.
TR. D2 is the second part. I mean, between the obstruction and R.
Sir.
So we just consider that it is this D1 and D2 have the same values
Oh, okay.
as you get when you measure the distances on the ground, when you don't have the inclination. Of course, this D1 and I mean it will be a little larger, but you just consider them to be equal. I mean, you may be given these values on the ground. Okay, in the question, but you just assume that they are equal here.
Okay.
So, okay, so for this path difference, del, okay, del is commonly used as a notation to indicate the path difference for wireless technologies. So del has this long expression. Again, if you do Taylor series expansion and do the approximation, okay, I mean, ignore the small components, then you just end up with this simple value for del. Okay, now we will show you the expression for PR, but that is something, well, I mean, some relationship developed or okay by others. It also involves some tests. Okay, so we will not theoretically actually just establish that this is the relationship to calculate PR. Rather, we'll show what has been derived. Okay, and as I said, that partly depending on tests, these relationships are derived. Now, for this relationship, you first have to calculate the power that you would get if you had a direct ray. That that you get for free space equation. Okay. So just consider the total distance. Okay, and you assume that there is a direct ray possible, like the free space equation, and using that free space equation, you calculate the power reception, that is P naught here. So P naught is the power calculated using free space equation. Okay. Then we will add something, GD. Okay, that will actually change the power content. So GD will have a negative value. You know that, I mean, your power reception will be much less. We don't have an, I mean, we have an abstraction. It's not possible that we get direct power from there. We'll just have the power diffracted. Out of diffraction, we'll get some power, and that will be definitely much less compared to what you would get if you had a direct ray. Okay. So you calculate P naught and then you add some negative value to find out what power you get when you have the obstacle. Okay. And of course, you also understand that if you have a higher tower, okay, then the diffracted ray will increase, right? If you increase the tower height, then your diffracted ray will increase, right?
Yes, sir.
But actually, it is not.
Oh.
I mean, apply your intuition. I mean, if you have just 100 uh, storied building,
Okay, so less obstructions, sir. So less
yeah,
different.
yeah,
Okay, okay,
100
okay, okay, sir.
right? So,
Yes, sir.
I mean,
My bad.
please don't agree with the teacher always. The teacher can be
Sir,
wrong, right?
can you say it again, sir? Again.
Yes,
I
sir.
mean,
I
if-
missed it also. Sorry, sir. My bad.
If you have a smaller height, okay, then you should get better diffracted power. If you increase the tower height, of course, I mean, out of intuition, we can say that, I mean, if I just make the tower height 10 times,
Mhm.
of course, our diffracted power will be less.
Obviously, yes.
Yeah, obviously less.
Because
So,
less obstructions. sir.
yeah.
It
Okay.
just
So
passes through.
when I ask you something, okay, apply your judgment. Don't agree with the teacher always. The teacher can be wrong. The teacher is a human being, right? So he can be wrong.
But sir, it has to travel a longer distance.
It has to travel, yeah, of course. I mean, couple of reasons. First of all, it has to cover a longer distance on both sides. Secondly, out of diffraction, you may get, I mean, the angle towards, I mean, your angle is increasing, right? I mean,
Yes, sir.
your angle is increasing. Okay, so that's the second reason. Okay, so height matters. D1 and D2, if I increase these distances, then that should increase or decrease the receive power.
Yes, sir. Say it again, sir.
The D1, well, will D1 and D2 impact the power reception? Consider the diffracted power.
Diffracted. It should depend on D1 and D2. D1 and D2, so this path is
Yeah,
greater,
of course, I mean, again, the signal is traveling longer.
longer. So
Yeah.
the longer the signal travels, the lesser
Yeah.
amount of power we get
Yeah,
at the receiver.
right. So they will impact. And finally, the frequency will impact because the
Angle of diffraction.
yeah, again, it will affect in two different ways. The angle of diffraction. Okay, I mean, this also depends on your frequency, and the distance that we have actually it finds in terms of how many wavelengths it's cover. Okay, that we discussed in the case of phase space equation. I mean, when you send signal towards some point, it's not how many meters or how many kilometers you have. It's like how many wavelengths you have on the way. Okay, that tells you how much signal decay you have, right? See here. Let's go back to our first discussion.
Sir, can I ask
Yeah.
something?
Yeah, just give me a second. See here, we have d by lambda. So this is very fundamental relationship. For all this is a free link, right? This equation is for a free link. And I discussed in the last class that you always have this free link possible, free link there. I mean, you may have many different things, but before and after these different things take place, like diffraction, reflection, or whatever, you have a free propagation. Then you hit something, right? So this one always actually affects somehow. And here what you have, d by lambda.
Sir, we can't see the new screen you have shared.
Oh, sorry. I'm sorry. In this case, you have d by lambda, right?
Yes.
So it always depends on how many d by lambda you have. Okay.
How many full oscillations are?
Yeah. So how many wavelengths you are covering? It's not actually the distance in meter or kilometers. Okay. It's like how many wavelengths you cover, right? So
Certainly,
that
why is it so? I mean, for each wavelength, each wavelength, to cover the each wavelength, we need to, if I think about wave that propagates through a medium, if I think about wave, so for each oscillations, the medium should be disturbed, and that's why the
no, it's
energy
because
that we are
it's not because of that. Okay, it's
so why?
because the signal is spreading out. It's because the signal is spreading out, and that is reducing the power level. I mean, this d by lambda relationship does not hold in all different cases. I mean, it's for this particular case where you have signal is spreading. I mean, for this free space equation. So here the signal is spreading out. So in that case, you have the relationship like d by lambda. Okay, how many wavelength you have here. So
Okay.
just okay, so you have to just measure how many wavelengths it is covering. So anyway, the wavelength does matter. So whatever we are thinking that we have the distances on the two sides, you have to consider, okay, in terms of lambda. So P depends on all these things, H, D1, D2, and lambda. But for this complex case, diffraction case, Fresnel, Kirchhoff, I mean, they proposed a single parameter, which includes the impact of all these four factors. Okay, it just incorporates the overall impact of H, D1, D2, and lambda for diffraction case. So it is called Fresnel-Kirchhoff diffraction parameter, and it is shown as nu. Okay, so I mean, this is the expression for nu. So what do? You just put all these values H, D1, D2, lambda, and find out nu. Okay, then use this nu to find out how the diffraction will affect. Okay, and how will it affect? Well, here, okay, the overall impact we are showing as G. Now this is the relationship. You calculate nu and use this graph to find out your G. Okay, so maybe if you have 2, if your nu is 2, then your G will be like minus 18 dB. Okay, all these are negative values, minus 18 dB. I told you before that G should be typically negative. It's minus 18. Okay, if it is 4, then minus 25 dB. Okay. So earlier you calculated P naught, okay, although you don't have direct ray. Then just subtract 25 from there or add minus 25. So that will give you the power that you get out of diffraction. Okay. So the job is very simple. I mean, in the exam, I may give you these values. You just calculate nu. This graph may be available in the exam. From there, you calculate G, and then calculate P naught first, then add, get PR. Okay. Now, I mean, there is an approximation of this graph also. Okay, so these relationships are given by Lee. It's called Lee's equations, where I mean you put the value of nu and calculate G using equations. But the equations depend on the value of nu. You first check the value of nu, which range it falls in, and use the corresponding equation to find out G. Okay, so this I mean this figure gives you more accurate value, and this has some approximation. Okay. So I mean in the exam, I mean it depends. I mean if I give you these equations, or if whatever I ask, just follow that. Okay. Well, I have a couple of more things to mention here. But let me first check if you have any questions. We have only
So
3
there is a
minutes.
ripple in the graph.
Mhm.
There is a ripple in the graph in the
There,
first.
yeah. This something.
So,
One of the two things is this one. I need to explain. Okay.
And from the ripple, I can see that in some cases, in some values of new, the gain is positive. I mean,
Right.
it's
Right.
actually getting more power
Yeah.
than the transmitter. But how is it possible?
Yeah. How's it? Okay. So let us discuss this part. Okay. Now I'll do that. Well, now see that new is positive here on this side. Above 0, we have positive values, right? I mean, new has positive values, but below 0, new has negative values, right? So how new can be negative? First, let's check. How new can be negative? Any idea?
So H must be negative.
H must be
There's a root.
negative,
So,
right?
oh,
So
root, that's a positive number.
to be
Root.
new negative, H has to be negative. What does that mean? What do you mean by negative H?
I mean, it H negative হইতে পারে না।
How can
So
H
there is a
actually be
direct obstacle free. There is a direct obstacle free path here, and
Right.
there is also a edge downwards. I mean, the
Yeah.
point is below TR. So there is a
Right.
there is one path.
Yeah,
directly
you're
from
absolutely right.
TR and
I mean, the obstruction is lower than TR. Obstruction is lower than TR. Then what would happen? The direct ray is possible then. The free space link
yes,
is possible. So unlike before, actually, you have that link too. You have a direct ray too. In addition to that, you have a diffracted ray, a ray from the edge of your obstruction. So when your H is negative, then you have two rays getting to the receiver, one direct ray, the other out of diffraction. Then it depends on the relative phase position, whether or not the overall or the resultant signal will be larger than your direct ray or smaller, right? The phase relationship. I mean,
yes, it depends on the
and this phase
phase.
relationship depends on the again on the distance, the paths they cover, right? So the paths they cover are actually
Yes.
indicated by nu. For different values of nu, sometimes it will be they will be additive, sometimes they will be subtractive, right? So first of all, if your H is negative, it is possible that you get something, I mean, you get direct ray and you get something more. So it is possible to have a positive value of G. It can be higher than P naught. It can exceed your direct ray value. But of course, then you have to have additive resultant here. But if it is subtractive, if you're, I mean, because of the phase difference, if diffracted ray is reducing, then it will be less than P naught. So depending on your, I mean, value of H or value of nu, okay, you will have sometimes positive, I mean, more than P naught or less than P naught. So there will be, we can expect some ripples here around, I mean, zero level indicates a value equal to P naught. But around that, you have positive or negative values depending on nu. Okay, there are ripples. So two things you can you should now understand that why positive values are also possible. Okay, and why we have some ups and downs there. It's an oscillation around zero. Okay, sometimes higher than P naught, sometimes lower than P naught. Okay, but all these cases have the obstruction height lower than the line connecting the transmitter and the receiver. Okay, 2 minutes over our actual limit. Any further questions?
Sir,
Yeah.
so in one class you discussed
Mm-hmm. Sorry.
Yes. So in one class you discussed about inter-symbol interference. This term in one
Right.
class
Right.
in the first or second class, I think.
Right. Right.
There you said that if there are multiple paths for the signal to transmit from
Right.
transmitter
Right.
to receiver. So
Right.
if they are in different phase, so
Yeah.
you will I mean
Yeah.
it will create a problem. So is
Yeah.
it this problem we are addressing to?
Yeah. You are absolutely right. Intersymbol interference can be there whenever you have signals combination as combinations from from signals via multiple paths. Now we will consider that we'll have more discussion on intersymbol interference when we consider the non-LS environment. There will be too many paths from there
That's available.
in that case. Okay, still we are actually, all these things are a part of non-LOS case. So far what we are discussing, say diffraction, reflection, penetration, all these things are part of non-LOS environment. So if you aggregate all of them, then you have it's just one component of one of the 100 components that you have in actual non-LS environment. In actual non-LS environment, the signal is a composition of maybe 100 components. Okay,
Mhm.
so we're just considering one of those components, a diffracted ray. But
Okay.
via many other paths, there'll be some reflected ray, there are some scattered component. So all these are arriving together and you sum up all of them. And then you have, each of them have different delays and there are possibilities of inter-symbol interference. Okay, so there's a complicated case. We will talk
Sure.
about that later. But of course, it's a very good question. It relates to this problem, ISI. Okay, clearly we have an indication of potential indication of ISI.
Sir,
Yeah.
could you, sir, even the class is finished, I just have to ask, sir, can you kindly explain, how the H is getting negative, sir? Like that part, sir, I couldn't understand. We told that mu is negative because H is getting negative.
Yeah,
right,
just
sir?
from this
So,
expression, look
yes,
at this expression. Look at the
yes, sir,
expression
this
of
is I
mu.
understand, but sir, how is the H is being, how is the H turning negative, sir? That part.
Well,
So you
in our
at least-
assumption, H is the height of the obstruction above TR, above the line connecting transmitter and receiver.
Yes, sir.
Here
Yes.
is the line connecting transmitter and receiver. So see, if H is plus 2 meters, then we have
Okay, so
2
if
meters
the line
above.
is above the obstacle,
Yeah.
then it is like, oh, okay, okay, okay.
If your tower height is lower than this line,
Yes, sir.
connecting, then H will be negative. Okay, we start measuring H from TR. Okay,
Okay, sir.
got
Okay,
it?
sir.
Okay. Any other questions? If not,
So sir, this is causing this is causing our the ripple that initially formed
yeah.
in that graph.
First of all, when it goes below that line, then you actually create a free path for your direct ray. Free space link is then open. Okay, you have a direct ray. In
Yes.
addition to that, so then the receiver gets 2 rays. It
Yes,
will
sir.
get a resultant of 2 rays. And
Oh,
okay,
thank you.
anything else
No, sir.
that I can help with? Okay, let's wrap up for today. Thank you for your time.
Sir,
Yeah.
for the lab today,
But there is no lab class today.
what?
In the next week, inshallah, we'll have our next lab class. Okay,
Okay.
for all of you, no lab class today. In the next week, every other week, we'll have a lab class, inshallah.
Okay.
Okay. Thank you. Wa alaikum assalam.